Okay, so imagine this. Your application, it's finally taking off, users are pouring in, it's the dream, right?
Absolutely.
But then, bam, servers start crashing, the whole thing slows to a crawl, and your team, they're just fighting fires, drowning in tech debt, not building anything new. How do you even start to build something that handles today and is ready for, a global audience tomorrow?
Yeah, that's the million-dollar question, isn't it?
Well, for this deep dive, we're digging into Artur Agesman's Web Scalability for Startup Engineers. It's from 2015, but honestly, the principles, still incredibly relevant. Think of it and us talking today as kind of your guide through this maze.
Right.
It really maps out how the software architecture side and the infrastructure side have to work together for real scalability.
And our goal here, for you listening, is to really pull out the key stuff from this book. We want to cut through the jargon, give you some solid, real-world advice, maybe even a few surprising bits you hadn't thought about. It's like a shortcut to getting properly informed on this whole scalability thing. The book itself aims to help engineers kind of level up their understanding.
Okay, let's start right at the beginning then. What is web scalability? Because it's more than just like handling tons of traffic. E.J. Asmont breaks it down really well. First, it's about handling higher concurrency levels. So more people using it at the exact same time without things falling apart for them.
Right, without slowing down.
Exactly. And the challenge there isn't just, raw server power. It's also managing limited CPU, threads, and keeping data consistent when loads of things are happening at once.
Yeah, that consistency bit is tricky.
And the second thing is higher interaction rates. How often are users actually sending info back and forth? A blog versus, say, a fast-paced online game? Totally different worlds.
Huge difference.
And the big hurdle there is latency. If interactions are happening super fast, the responses have to be instant, which pushes concurrency needs even higher.
And one thing the book touches on, which often gets missed, is that scalability isn't just tech specs. It's tangled up with how you develop, how your teams are set up, even how your code is structured.
Yeah, interesting. The human side.
Exactly.
Yeah.
You could have the fanciest tech, but if your team process is a mess, forget scaling. That organizational bit is just as crucial.
So how does an app typically grow? The book traces this path, right? From like one server under a desk
Oh yeah, we've all been there.
to maybe thousands globally.
Yeah.
Usually starts simple. Single server setup, everything database, web server, files all in one machine.
Super simple.
DNS points users there. Maybe you start with a VPS, a virtual private server. Cheap, easy to upgrade.
Yeah, common starting point.
Then when that one server starts sweating, the first move is usually vertical scaling. Literally make the server stronger. More RAM, better CPU, faster network. Simple, right? No code changes needed. Just upgrade the hardware. Instant power boost.
But here's the catch, and it's a big one. The cost. That price per capacity unit, as the book calls it. It shoots up exponentially after a point.
Ah, okay. Diminishing returns.
Totally. You pay way more for less and less gain. It becomes unsustainable pretty quickly for serious growth. You're just delaying the inevitable need to change the architecture.
So once you hit that vertical wall, the next little step is isolation of services.
Right.
Moving things onto separate machines, like web server here, database over there. Still pretty simple, but it's the start of distributing the load.
A slight evolution, yeah.
Okay. But for the really big growth, the sustained stuff, you need horizontal scalability.
This is the key.
Adding more servers, clones, basically, to share the load instead of just making one server massive.
Exactly. And while, yeah, maybe the initial setup is a bit more complex, maybe cost a bit more than that first vertical bump, it becomes way more cost-effective when traffic really ramps up. Think cloud providers, they offer lower costs per unit because they're built for this distributed model. Economies of scale kick in.
Right. But the book warns that getting true horizontal scaling across everything, that's hard and expensive.
Oh, yeah. It's a real engineering challenge.
So the advice is pragmatic. Start where it's easier. Web servers, caches. Tackle those first before you try and horizontally scale, say, your main database.
Definitely. Baby steps. Then, as systems get even bigger, you see multi-data center deployments.
Going global.
Pretty much. You use things like GeoDNS to send users to the closest data center. Someone in Europe hits European servers. Someone in the US hits US servers.
Makes sense, faster for them.
Way faster.
Yeah.
And you use CDNs, content delivery networks, for static stuff images, CSS, JavaScript. They serve those files from servers physically close to the user, cuts latency way down, saves on network costs too.
So if you look inside a really big web app, it's not just servers anymore, it's this whole ecosystem. Load balancers directing traffic, separate web app servers, web services doing the logic, different data stores, message queues.
Queue workers processing those messages, it's a whole orchestra.
Let's zoom in on the front-end layer then, the user interface. The book says its job is just presentation, keep it dumb.
That's the ideal.
All the heavy lifting, the business logic, lives somewhere else. That way the front end can be reused, scaled on its own.
And to make that dumb front end work, you have to understand stateless versus stateful services. This is critical.
Okay, break that down.
Stateless means any server can handle any request because it doesn't remember past interactions, like your login info.
Yeah.
It shouldn't live on the web server itself.
Right, because the next request might go to a different server.
Exactly. So you store that session state somewhere else, maybe in a cookie or better, in a separate super fast data store. Think Memcached, Redis, maybe DynamoDB, Cassandra things built for quick key lookups.
Got it.
And the book kind of warns against sticky sessions on load balancers, where it tries to always send you back to the same server.
Yeah, seems convenient.
It seems convenient, but it often just papers over bad design in the app itself and makes true auto-scaling, adding and removing servers on the fly, really difficult.
Okay. What about user files, like uploads?
Right, user-generated content. The strong advice is don't try to build your own fancy distributed file system.
Yeah.
Use third-party services like Amazon S3 or Azure Blob Storage.
Why is that?
Because they handle the high availability, the scaling, all that complex stuff transparently.
Yeah.
Building that yourself is, well, it's a huge, complicated undertaking. Let someone else solve that problem.
Makes sense.
And other state-like things, local server caches, maybe some in-memory application state, resource locks on one machine, those also kill scalability. Push that stuff out to shared caches, shared lock services. Keep those web servers stateless.
Okay, so if you have all these stateless servers, how do you get traffic to them evenly? Load balancers, right?
Yep, absolutely essential for horizontal scaling. They sit out front, spread the requests around.
So everyone gets a fair share of the work.
Exactly. And it means you can add more servers easily, or if one fails, the load balancer just stops sending traffic there. Seamless failure handling.
The book mentions DNS round robin as a simple way.
Yeah, it's basic, just cycles through IP addresses.
Yeah.
But managing it, adding or removing servers means DNS changes, which can be slow to update everywhere.
Right. So better options are dedicated load balancers, like expensive hardware ones.
F5, Citrix NetScaler, those big boxes.
Or more flexible software-based ones like Ninjinx or Hrep proxy.
And Jinx is particularly cool because it can also act as a reverse proxy and a cache layer itself, taking load off your actual application servers. It's a real workhorse.
And for the web server tech itself, PHP, Python, Ruby, Node.js, does the choice matter hugely for scaling the front end?
The book suggests that as long as those front-end servers are properly stateless, the specific language choice matters less for pure horizontal scalability.
Interesting.
Though it does call out Node.js as being particularly good at handling loads of simultaneous open connections. So for real-time stuff, chat apps, that kind of thing, it has an edge.
Okay, now here's something that sounds like magic. Auto-scaling.
It kind of is. It's automating adding and removing servers based on actual traffic and load.
So it grows when busy, shrinks when quiet.
Exactly. Huge cost saver. You're not paying for idle servers during quiet periods. It relies heavily on cloud stuff like Amazon EC2 for the servers, ELB for load balancing, CloudWatch for monitoring the load.
But the key is those web servers have to be disposable, right?
Absolutely. You need to be able to spin them up or shut them down instantly without anyone noticing. Stateless is key.
So practically, how does this compare, say, deploying on AWS versus running your own private data center?
Big difference, especially for startups. AWS gives you all these managed services, Route 53 for DNS, ELB, S3, CloudFront CDN. It handles so much of the infrastructure pain for you.
Frees up your engineers.
Totally. They focus on the product, not racking servers. A private data center. That's a lot more hands-on management. More control, sure. And maybe it makes sense for huge companies with very specific needs, but it's a massive investment in time, money, and expertise.
All right, let's move deeper into the stack. The web services layer. The book calls this the critical layer, holding most of the business logic.
Yeah, it's the brain, essentially. And decoupling it from the front end is key for scaling both independently.
How does that logic usually get organized? Starts as one big app.
Often, yeah. Monolithic applications, all the code in one place. Simple at first, but gets really hard to manage and slow to change as the team grows.
So what's the fix?
The move towards an API-first approach. Instead of logic scattered everywhere, you centralize it behind a clean API. Then your mobile app, your website, third-party partners, they all talk to that same API.
Avoids duplicating logic everywhere.
Yes, exactly. Less code, more consistency. Now, the book is pragmatic. It says think about services from day one, design for it, but maybe don't actually build separate microservices until the complexity really forces your hand.
Okay. And how do these services talk to each other? Protocols like OOP and REST.
Those are the main contenders discussed. OP is very formal, uses XML, has these strict contracts with WSTL and XSD, good for very formal enterprise integrations like banks.
Sounds complicated.
It can be. And historically, the tooling for dynamic languages wasn't great. It felt heavy, especially for startups moving fast.
So the alternative is REST.
Right. REST is much simpler, uses JSON, standard HTTP methods like get, post, put, delete. It feels more natural for the web. And crucially, REST plays really nicely with HTTP caching, which is a huge scalability win.
We'll definitely come back to caching. But what are the tricky parts when building these scalable web services?
A couple of big ones. Distributed locking. When multiple services need the same resource, using locks causes delays, dependencies, risk of deadlock.
Yeah.
It gets messy fast.
So avoid locks.
If you can, the share nothing idea is best. Look at alternatives like optimistic concurrency, assume it's fine. Fix conflicts if they happen, or use message queues. Another beast is distributed transactions.
Making sure multiple steps across different services either all succeed or all fail together.
Exactly. Things like two-phase commit. It guarantees consistency, but it's complex and really hurts availability. A more scalable approach is often compensating transactions, basically letting things happen, and then having automated ways to undo or fix things asynchronously if something goes wrong later.
Okay, you mentioned HTTP caching for REST services. Why is that so important here?
Because if you can cache the result of a web service call, you save a huge amount of processing. But, and this is critical, your GET request must be truly read-only.
Meaning they can't change anything.
Not a thing. No sneaky database updates, no changing state, not even writing a log entry that accidentally affects something else. If GET teaches state, your caching is broken.
Got it. And how does breaking the monolith into smaller services help scaling?
That's functional partitioning. Splitting the big system into smaller, focused, loosely coupled services. Each does one thing well.
Like a billing service, a user profile service.
Exactly. Reduces dependencies, lets different teams work independently, and here's the scaling when you can scale each service based on its specific needs. The user profile service might need way more read capacity than the billing service, for example. It's the path towards a service-oriented architecture, or SOA.
All right, let's brace ourselves. The data layer. The book calls this usually the most challenging area.
Often is, yeah. Especially now with the sheer volume of data and users we see.
Where do most people start? MySQL.
Still very common. And the first scaling technique is usually replication, specifically master-slave.
Okay, what's that?
You have one main master database that handles all the writes. Then changes get copied asynchronously to one or more slave replicas.
And the slaves handle?
Reads. You spread the read load across the slaves. Plus, you can back up a slave without impacting the master. If a slave dies, no big deal, take out of rotation.
Sounds good. What about master-master?
More complex. Two masters write and replicate to each other. Can be used for faster failover if one master goes down, or for easier maintenance.
But there's a catch, right? You mentioned asynchronous replication.
Big catch. You lose that single source of truth. Because it's async, there's a delay. So at any given moment, the two masters might not have the exact same data.
Eventual consistency.
Exactly. It'll get consistent eventually, but not instantly. That's a fundamental trade-off.
And replication doesn't solve everything.
Critically, no. Replication helps with read load, but it does not solve the problem of your active data set just getting too big for one server.
What do you mean by active data set?
Think e-commerce purchases, heavily used for a bit, then fade. But music playlists. People access their whole list all the time. That active set just keeps growing. Replication doesn't shrink the total data size on the master.
So if your data just gets too big for one machine, even with replicas...
Then you need data partitioning or sharding.
Splitting the data up.
Exactly. You divide your data into independent chunks or shards, maybe based on user ID or geographic region. Each shard lives on its own server or set of servers. It's a share-nothing approach, ideally. No communication needed between shards.
But that sounds complicated, too.
It is. Choosing the right sharding key is hard. A simple formula might make adding new servers later a nightmare. And running queries across different shards, that can be really slow and complex. How do you find a user if you don't know which shard they're on?
Tricky.
One tip the book mentions is using logical shards on fewer physical servers initially. Makes it easier to just move a logical shard to new hardware later without resharding everything.
Okay, this complexity sounds like why NoSQL data stores became popular.
Exactly. They were born out of the need for massive scale that traditional relational databases struggled with. They typically trade things like flexible joins and rigid schemas for better scalability.
And it requires a different way of thinking.
Totally. The book stresses this. With NoSQL, you often start designing with your queries in mind, not just the data structure. How will you need to access the data? Optimize for that.
This brings up the CAP theorem, doesn't it? Consistency, availability, partition tolerance. Pick two.
The classic trade-off in distributed systems. You generally can't have all three perfectly when the network gets unreliable, which it always does eventually.
So examples.
Well, DynamoDB often prioritizes availability and partition tolerance, AP, meaning it stays up even if nodes disagree temporarily. That's eventual consistency. MongoDB often aims for consistency and partition tolerance, CP, trying to ensure data is right, but historically had quirks where data could be lost if replication wasn't set up perfectly. Cassandra is generally AP, focusing on availability and scaling, also with eventual consistency and great self-healing.
So that choice availability over immediate consistency, or vice versa, is fundamental.
It defines how your system behaves under stress, absolutely.
And eventual consistency. It means users might see slightly old data sometimes.
Potentially, yes. Or conflicts might arise if two people change the same thing at once on different replicas, but the system stays available. You then need strategies to resolve those conflicts later.
And NoSQL isn't just one thing, right? Different model.
Right. Key value stores, document stores, wide column stores like Cassandra. Let's take that option side example with Cassandra. To make queries fast, you'd probably denormalize heavily.
Meaning duplicate data.
Yep. You might store bids in a user bids table, optimize for showing a user their bids, and in an item bids table, optimize for showing bids on an item. Reading is super fast for those common queries.
But updating gets harder, like changing a username.
Much harder. You might need an offline job to find and update that username everywhere it was duplicated. It's a trade-off, read speed versus write complexity.
So it sounds like the trend is using multiple types of databases.
Definitely. Polyglot persistence is the right tool for the job. Relational for some things, NoSQL for others, maybe a search engine too. More flexible, more performant, but yeah, adds complexity to manage it all.
Okay, let's shift gears to something potentially less complex but hugely impactful. Caching. The book calls it the supreme art of war.
Yeah. Subdue the enemy without fighting. Serve the request without actually doing the work again.
How does it boost scalability so much?
By drastically reducing the load on your expensive resources, your application servers, your databases. If you can serve a request from a cheap cache instead of recomputing or refetching, you win big on performance and capacity, often at low cost.
So how does it work, basically?
Simple idea. Do the work once, store the result temporarily in the cache, and serve future identical requests from that cache until it expires or gets invalidated.
And the key is the cache hit ratio, how often you actually find it in the cache.
Exactly. That depends on a few things. How often the data is accessed, popular stuff cache as well, the size of your cache, usually limited by expensive memory, and how long the data stays fresh, its time to live, TTL, or explicit invalidation.
Let's talk HTTP-based caching. How does that fit in?
This is caching that happens between the user's browser and your server. Think proxy servers. They intercept requests and might serve a cached copy instead of bothering your application.
And you control this with HTTP headers, like cache control.
Precisely. Cache control is your main tool. Max age tells caches how long they can reuse the response without checking back. Public means proxies can cache it. Private means only the user's browser should. No store means don't cache it at all. No cache means check back before using the cached version. And the very header tells caches that the response might differ based on things like language preference.
What's the ideal scenario here?
For static stuff images, CSS, JS files, the dream is to cache it forever. You do that by giving new versions a completely new URL. The old URL never changes, so caches can keep it indefinitely.
Ah, clever.
And a key benefit of REST services we mentioned, they can leverage all this HTTP caching goodness too. Caches exist everywhere. Browser cache, ISP caches, CDNs, and your own reverse proxies like Nginx.
How do you scale those caches?
For static assets, you push them to a CDN. They handle the scaling globally, transparently. For your own reverse proxies, you run multiple instances in parallel behind your main load balancer. They operate independently.
Okay, what about caching inside the application? Application object caches.
Right, closer to the code. You've got client-side caches, browser local storage, or session storage where JavaScript can stash data, reduces server requests.
User-specific stuff.
Yeah. Then co-located caches where maybe each web server runs its own local cache, like memcached. Prepares you for distributed caching, but duplicates data. And finally, distributed caches, separate clusters running memcache or Redis.
More memory, more throughput there.
Way more. And crucially, these are often easier to scale than databases because the data is disposable. If the cache dies, you can rebuild it from the source. Consistency and persistence needs are much lower. Scaling them often involves partitioning data across nodes, maybe client-side, and sometimes replication for high availability.
So any quick rules of thumb for caching?
The book gives a few good ones. First, cache as high up the stack as possible. Browser CDN, reverse proxy app, cache database. Closer to the user is better.
Saves more work down the line.
Exactly. Second, avoid complex cache invalidation logic. It's a nightmare to debug. Simple TTLs are often way easier to manage.
Makes sense.
And third, maybe use shorter TTLs for things that change often, or use a hybrid approach, cache the main chunk of data, but fetch the really volatile bits live, balance freshness and performance.
All right, next big topic, asynchronous processing. The book paints this as a different way of thinking.
It really is. Instead of strict step-by-step code that waits.
Blocking.
Yeah, blocking. Instead, you break work into smaller pieces and let the system figure out when and how to run them. Non-blocking.
Give me an example.
Okay, sending an email. Synchronous.
Okay.
Your code calls the email service and just waits there until the email is sent. It's stuck, consuming resources.
Oh, yeah.
Asynchronous. Your code calls the email service, which just puts an send email message onto a message queue, and your code immediately continues doing other stuff.
Ah, like dropping a letter in a mailbox. You don't wait for the mail carrier.
Perfect analogy. The queue acts as a buffer. You have message producers putting messages in and message consumers pulling them out and doing the work later.
And they're decoupled.
Massively. The producer and consumer only need to agree on the message format and the queue name. They don't even need to know about each other. The message broker, the queue system itself, handles storing, routing, delivering the messages.
Routing, like different types of queues.
Yeah, common patterns are point-to-point. One message goes to one consumer, good for big tasks like video processing or publish subscribe, where one message goes to multiple consumers, good for notifications.
And the consumers themselves.
Those are typically queue workers, dedicated servers, usually stateless, just pulling the queue for work. And you can scale them independently. Need faster email sending. Add more email queue workers.
Sounds powerful. What are the gotchas?
Well, message ordering isn't usually guaranteed, especially with multiple workers.
So create user might get processed after send welcome email.
Could happen. You need to design for that possibility, assume random order, or use specific queue features if they offer partial ordering. Another big one is message requeuing.
Getting the same message twice.
If something fails during processing, the broker might redeliver it to ensure it gets done. So your consumers must be idempotent.
Meaning they can run multiple times with the same input, but produce the same results.
Exactly. Sending 2 welcome emails is bad. Setting a user status to active twice, no harm done. Idempotency is crucial for reliability.
Okay. Anything else? Dead letters.
Yeah, dead letter queues for messages that consistently fail. And documenting the flow is vital because it can get complex. Also, a strong warning. Don't couple producers and consumers directly. The broker and the message are the contract.
How do you choose a queue system? Cloud like Amazon SQS versus running your own?
SQS is great for startups. Zero management overhead, pay as you go, saves huge amounts of time initially.
Downsides.
It's pretty basic. Size limits, simple routing, and critically no guaranteed ordering.
And self-managed. RabbitMQ, ActiveMQ.
More features, more flexibility, often higher performance. RabbitMQ is very popular, flexible routing. ActiveMQ is Java-based, embeddable, but you have to manage them. And they don't scale horizontally out of the box like SQS does. You usually need to do application-level partitioning to spread the load across multiple broker nodes yourself.
Okay. And this all leads towards event-driven architecture, EDA.
It's a related concept, yeah. With EDA, components don't request work. They announce events that have already happened. Order placed. User updated.
How does that help?
It reduces coupling even further, and components just react to events they care about, lowers the dependencies, enables cool things like event sourcing, rebuilding state by replaying history, and you can often introduce it gradually.
Interesting shift in thinking. Okay, another area, effective data searching. Finding stuff in huge data sets.
Yeah, terabytes of data.
Yeah,
Simple database queries aren't enough. The key tool is indexing.
like a book index.
Exactly like that. A separate data structure optimized for lookups. Instead of scanning the whole table, ON, you use something like a binary search on the sorted index. Again, massively faster.
So for a billion rows, instead of a billion checks, it's like 30.
Roughly, yeah.
Yeah.
Huge difference. Now, what makes a good index column is cardinality, the number of unique values. High cardinality, like user IDs. Great for indexing, narrows the search fast. Low cardinality, like gender. Not very helpful.
What about indexing multiple columns, compound indexes?
Useful, but the order of columns in the index matters a lot. You need to optimize it for how you actually query the data.
And how does NoSQL data modeling fit into search? You said design for the queries.
Right. Comes back to that. You might denormalize data specifically to make certain searches fast, even if it feels wrong, coming from a relational background.
Like the auction site example, storing bids in two places.
Exactly. User bids for finding a user's bids quickly, item bids for finding an item's bids quickly. Duplication optimizes those specific search patterns, even if updates get more complex.
But what if you need really flexible text search, things databases struggle with?
That's where dedicated search engines come in Elasticsearch, Apache Solr. They're built for this.
How do they work?
Their core is usually an inverted index. They break down text into words, tokens, and map each word back to the documents containing it. Just like a book index maps keywords to pages. Super fast for text search.
Manage them yourself or use hosted services?
Hosted services, Splunk, Logi, cloud options often make sense to avoid the operational headache. But open source like Logstash is powerful if you self-host. And keeping them synced, often done asynchronously via a job queue. Database change triggers a message. A worker updates the search index.
Okay, we've covered a ton of tech. But the book stresses the other dimensions too. Processes, teams, code structure, the human side again.
Hugely important and often the real bottleneck. First thing to automate. Automated testing.
Why so critical?
Manual testing just doesn't scale. Its cost grows way faster than the cost of writing automated tests. Good tests give you confidence to change things quickly, refactor, speed up development cycles massively. Unit tests, integration tests, end-to-end tests.
Tools like JMeter, Selenium.
Yeah, for performance and browser testing. Then, automate your build and deployment processes.
Avoid those scary big bang manual releases.
Exactly. Manual releases get bigger, riskier, slower, a vicious cycle. Automation enables a positive cycle. Frequent, small, low-risk releases leads to continuous integration, CI, continuous delivery, CD, even continuous deployment, CD, where code goes to production automatically minutes after commit.
That's the dream.
It really changes the game. And alongside that, monitoring and alerting. This is about increasing availability by cutting down mean time to recovery, MTTR, when things do break.
How does MTTR break down?
Time to discover the problem, time to respond, time to investigate, time to fix. Automation slashes the first three. Automated alerts tell you instantly.
What should you monitor?
Infrastructure metrics, CPU, RAM, application metrics, error rates, latency, business metrics, signups, revenue, external SLAs. And log aggregation tools like Splunk, Logstash help massively with the investigate part. Searchable logs are gold.
This all sounds like it boosts productivity.
It does, but productivity isn't just tools. The book warns strongly against overtime as a scaling strategy.
Leads to burnout.
Totally. Bad code, mistakes, people leave. It's unsustainable. Managing productivity is about making smart trade-offs, the project management triangle.
Yeah.
Scope, time, cost. You can't fix all three.
So how do you manage scope without killing morale?
Prioritize ruthlessly based on value. Use data if possible. Lean startup thinking, not just gut feelings. Apply the 80-20 rule. Is this feature good enough? Don't gold plate things. Avoid you ain't gonna need it features. Aim for good test coverage, like 85–90%, not necessarily 100%, which costs a fortune for little gain.
Other productivity tips.
Delegate effectively. Share knowledge through pair programming, code reviews, split work into small deliverable chunks, and use mocks or prototypes, quick, cheap ways to test an idea's value before building the whole thing.
Great ideas. Finally, scaling teams. More people doesn't always mean faster.
Definitely not. Communication overhead explodes. The number of connections grows quadratically. Suddenly, everyone's in meetings.
So smaller teams.
Smaller cross-functional teams organized around products or services. Like a checkout team has engineers, product design, QAA. Everyone needed to own that experience. More autonomy, fewer dependencies between teams.
But you still need some standards.
There's a balance. Standards versus autonomy and innovation, but the absolute key is alignment. Everyone pulling in the same direction. That requires a culture of humility, respect, trust. Company first, then team, then individual. That's how you truly magnify strengths.
Wow. Okay, that was a whirlwind tour of web scalability. We went from the basics of concurrency and interaction rates through the whole evolution from one server to global setups.
Vertical versus horizontal scaling, data layers, sharding, NoSQL, CAP theorem.
Caching strategies, asynchronous processing, message queues, event-driven ideas, searching techniques.
And then, crucially, automating tests and deployments, monitoring, managing productivity smartly, and scaling the teams themselves.
It really is a vast landscape.
It is. So maybe the final thought for you listening is this. Scalability isn't a single target you hit. It's this ongoing journey of making informed choices, balancing trade-offs.
Yeah.
So looking at your own systems, your own work, through this lens, what could benefit from a fresh look? Which principles or techniques, maybe even the team or process ones you've overlooked, could make a difference? Because really, the choices you make today, they directly shape what's possible for you tomorrow.